In this exact moment, while your eyes move across this sentence, something almost nobody on the planet is thinking about is unfolding in complete silence. A metal object, no bigger than a small car, is drifting through space where nothing built by human hands has ever traveled before. No probe has reached it. No model has ever predicted what actually exists there. This object is not new. It was assembled before smartphones, before the internet, before most scientists who now study its readings were even born. It survives on about 4 watts of electricity, less power than the small bulb inside your fridge. This aging machine, one only ever meant to function for 5 years, is right now sending back information that is quietly rattling the foundations of modern physics. The people analyzing its signals aren't calling it curious anymore. They're calling it stunning, inexplicable. They're saying, on the record, that they got it wrong. This is the story of Voyager 1. Here's what headlines refuse to mention. It isn't only what this spacecraft found far beyond our solar system that should unsettle you. It's what that discovery might mean for life on Earth right now. It's also what is happening to this machine this very moment in 2026. Something almost nobody outside a small circle of engineers is discussing. And it's a specific date already fixed on the calendar, a milestone no human civilization has ever crossed before. Stay with this story because once you understand it fully, you will never look at the night sky the same way again. Let's rewind to where it began. It was September 5th, 1977. A rocket lifted off from Kennedy Space Center in Florida, carrying a spacecraft named Voyager 1. Its assignment was simple. Fly past Jupiter, fly past Saturn, snap some photographs, gather a handful of readings, then coast into the emptiness and go silent forever. Engineers gave it 4 years to live, maybe 5. NASA quietly penciled in the mission's end for around 1981 or 1982. It was supposed to be a tidy errand to the outer planets, a postcard from the edge of our neighborhood, and nothing more. What actually happened became one of the most remarkable chapters in exploration history. Voyager 1 did not fade into silence on schedule. It swept past Jupiter in March 1979, beaming back the first close-range photographs of that giant planet any human had ever seen. It swung by Saturn in November 1980 and kept going, picking up speed with every flyby, using each planet's gravity like a slingshot to hurl itself farther into the dark. By the end of the 1980s, it had traveled farther from home than anything our species had ever launched into space. And it was still talking to us, still running on circuitry today's engineers examine with disbelief. Then, in 2012, 35 years after liftoff, something happened that turned this modest mission into something enormous. Voyager 1 crossed the heliopause. If that word means nothing to you yet, understand this. It is arguably the single most consequential boundary in our cosmic backyard, and passing through it is the equivalent of walking out the front door of everything humanity has ever called home. Picture it like this. Our sun does more than warm us. It constantly throws off charged particles known as the solar wind, inflating a colossal protective bubble around our entire solar system. Inside that bubble sits every planet, moon, asteroid, spacecraft, and living creature that has ever existed. The outer skin of that bubble, where the solar wind finally loses strength and gets pushed back by pressure from outside, is called the heliopause, the literal edge of our solar system. Everything inside belongs to us. Everything past it belongs to something else entirely. In 2012, Voyager 1 crossed straight through that skin and emerged on the far side, becoming the first human-made object in history to leave our solar system, not symbolically, the first physical thing our species has ever sent into the true space between the stars. And it just kept broadcasting. Sit with that. We currently have a working instrument parked in interstellar space, not circling a planet, not near the boundary, but actually inside the cold, ancient darkness between star systems, a region no telescope or model has ever observed from within. And it's sending back a play-by-play of what that place is genuinely like. What it's telling us is nothing like what anybody expected. Here's the story's first sharp turn. Long before arriving out there, physicists had spent decades building rigorous, peer-reviewed models of what interstellar space ought to look like. Nearly all agreed. It should be calm, smooth, mostly uneventful, a cold, sparse environment where particles drift lazily and little happens. A quiet waiting room strung between solar systems. Voyager 1 walked into that supposedly calm room and found it closer to a raging storm. Starting in 2017, the plasma wave detector aboard Voyager 1 began picking up something nobody had anticipated. A steady, narrowband hum, faint but unrelenting, running through the plasma in a way no existing model allowed for. This wasn't a glitch. It was a continuous signal, persisting year after year across a stretch of space spanning more than 900 million miles, 10 times the distance between Earth and the Sun. The team studying this data, published in the peer-reviewed journal Nature Astronomy, reached a striking conclusion. Interstellar space is not the flat, uniform void the textbooks described. It's turbulent with structure at every scale, from meters to millions of miles. Alive with motion that had been invisible, simply because no instrument of ours had ever sat inside it before. Every model ever built to describe space beyond our solar system was constructed from the outside, using telescopes and theory alone. Now, for the first time, the one instrument we physically placed inside interstellar space is telling us those models missed something fundamental. The universe past our doorstep is stranger and far more structured than anyone realized. This is where the story stops being abstract and starts feeling personal. None of these findings stay safely out there. They circle back and touch us. The same bubble separating our solar system from this chaotic environment is the bubble shielding life on Earth. The heliopause isn't just a line on a diagram. It's a shield, deflecting dangerous cosmic radiation from distant stellar explosions before it reaches the inner solar system. If that shield is weaker or less predictable than assumed, the consequences for biology here could be significant. And Voyager 1 is telling us the interstellar environment pressing against it is far more turbulent and energetic than our models accounted for. We don't yet know what that means long term, but having to ask the question at all marks a real shift in how we understand our own fragility as a species. The story only gets stranger because we need to talk about what nearly happened in 2023. Voyager 1 very nearly went dark for good. For 5 straight months. It kept transmitting, but what it sent was nonsense. Scrambled data that engineers at NASA's Jet Propulsion Laboratory, despite decades of experience, simply could not decode. The machine was alive. The signal was arriving. But whatever it was trying to say had become unreadable gibberish. For a team running this mission since 1977, nothing like it had ever happened. The cause, once tracked down, was as simple as it was alarming. A single memory chip inside the flight data system had physically degraded after decades of bombardment by cosmic radiation. One tiny piece of 1970s hardware had developed a fault, scrambling the software responsible for sending data home. No warning flashed. It had simply worn out after 46 years, in the harshest environment any human-built object has endured. Ordinarily, you fix a broken part by reaching it. Here, that part sat roughly 15 billion miles away, unreachable by any known travel. The only tools were radio waves at light speed, taking 22 hours to reach the spacecraft one way, meaning every diagnostic step demanded 44 hours to complete a single exchange. Picture that from inside mission control. Examine the data, form a hypothesis, draft commands, transmit, wait 22 hours, study the response, revise, send again, wait again. Repeating that cycle patiently for months, knowing one mistaken instruction across 15 billion miles could kill the mission with zero chance of recovery. The team at JPL pushed through this for months. Under pressure most engineering projects never face. They pulled it off. The damaged code couldn't be repaired, but it could be relocated. Broken into pieces, stored across different sections of memory, each checked and rewritten, then stitched back into a working whole. It was, in effect, remote brain surgery through a 44-hour delay on a machine nearly 50 years old, 15 billion miles away. By mid-2024, Voyager 1 was back online, transmitting clean data again, and the first thing it sent back was more evidence of those unexplained plasma oscillations. A spacecraft that should have died in 1981 had clawed its way back with even more to tell us. But none of that, not the discovery, not the near-death experience, not the recovery, quite prepares you for what Voyager 1 actually found the moment it crossed the heliopause back in 2012. This is the part of the story where the scientific papers stop reading like ordinary physics and start reading like something else entirely. For decades, models predicted a gentle handoff at the heliopause, solar wind fading on one side, interstellar medium appearing on the other, like a river easing into the sea. That's not what Voyager 1 found. Particles weren't calmly thinning out. They were slamming into each other at speeds approaching a fraction of light speed, generating temperatures near 30,000 degrees Celsius. Not inside a star, but at the outer edge of our own solar system, a region supposed to be cold and sparse. Some scientists have called this zone a wall of fire, not as flourish, but as a genuine concentration of ultra-energetic particles, forming a real barrier at the edge of everything we call home. Then came the magnetic surprise. One bedrock assumption held that the magnetic environment would shift sharply at the heliopause, the sun's field inside, the galaxy's separate field outside cleanly divided. Voyager 1 found the opposite. The fields on both sides were actually linked, interacting through a process called magnetic reconnection, where field lines from different sources tangle and release energy. Our solar system and the galaxy are not magnetically isolated, they're connected. Energy is constantly being traded across that edge in ways no model had anticipated. This is not a small footnote. If our solar system's relationship with interstellar space is more dynamic and energetic than assumed, our whole understanding of how the heliosphere shields Earth over geological time needs rebuilding. Now to what's happening this very year, in 2026, because this story is far from finished. It may be entering its final act. Earlier this year, NASA made a call nobody wanted to make. The low-energy charged particle instrument, gathering data almost continuously since 1977, was powered down. Not because it failed, it was working perfectly. It was switched off because Voyager 1 is running low on power. Voyager 1 draws electricity from 3 radioisotope thermoelectric generators, containers of plutonium-238 producing heat as the material decays, converted into electricity. At launch, they produced about 470 watts. Today, nearly 49 years later, they're down to roughly 250, losing about 4 watts a year. Sometime in the early 2030s, output will dip below the threshold needed to run anything, and Voyager 1 will fall permanently silent. The mission team has seen this coming for years, carefully mapping out which instruments to retire and when, squeezing every drop of value from a shrinking power budget. Of the 10 instrument packages Voyager 1 launched with, 7 have already gone dark. Each decision is among the hardest any research team makes. Every instrument lost means questions that will never be answered, with no way back once you've decided too soon. But here's the twist almost nobody outside JPL is talking about. Now, they haven't given up on buying more time. Engineers are testing something reportedly nicknamed the Big Bang procedure, rerouting how power flows across the spacecraft's remaining systems to squeeze extra capacity from underused components. It's technically delicate and risky, since even small adjustments on a nearly 50-year-old spacecraft with no manual override could produce unpredictable results. So they're testing it first on Voyager 2, which has more spare power and sits closer to Earth. If those trials confirm it's safe, the same fix gets attempted on Voyager 1, with the earliest attempt no sooner than this coming month. If it works, the instrument just powered down could switch back on. Nobody's promising anything. But with Voyager 1, betting the story is finished before it actually is has never once been the smart wager. Now we arrive at a date already locked into the calendar, one no civilization has ever reached before. On November 18th, 2026, at 2:16 a.m. Pacific Time, Voyager 1 will reach a distance of exactly 1 light day from Earth. A signal moving at light speed will take a full 24 hours to reach it. Send a command Monday morning, and you won't know it arrived until Tuesday, and won't hear back until Wednesday. 2 full days for one exchange. No human-made object has ever been that far from home, and it will cross that threshold while still alive and transmitting. Then it keeps going, pushing roughly another 38,000 miles deeper every hour. The lag keeps stretching, the power keeps shrinking, and sometime in the 2030s, the last signal will arrive. But even after that, Voyager 1 doesn't stop. There's nothing out there capable of stopping it. No friction, no atmosphere, no gravity strong enough to bend its path. It will simply keep drifting, silently at roughly 38,000 miles per hour, into a darkness with no end on any timescale a human mind can comfortably grasp. Bolted onto its frame, riding along on this dying machine is something destined to outlast all of it. The Voyager Golden Record. A gold-plated copper disc carrying greetings recorded in 55 human languages. The sound of rain falling through a forest canopy. Ocean waves rolling onto a shore. Human laughter. 90 minutes of music pulled from cultures spanning the sweep of human history. Diagrams laying out the basics of our physics and mathematics. And a map, built from pulsar positions, meant to show anyone who finds it exactly where our small planet sits. Carl Sagan, one of the minds behind the record, once described it as a message in a bottle tossed into the cosmic ocean. And that's precisely what it is, because whoever eventually stumbles across it, another civilization a million years from now, or some intelligence we cannot yet imagine, the record will tell them something true, that a species once lived here, that they were curious, that they reached outward, that they built a machine out of metal, electricity, and mathematics, and sent it beyond everything they had ever known, carrying the sound of their own laughter. That record will still be drifting long after the sun swells into a red giant and swallows Earth's orbit whole, long after every human city, every archive, every name we ever carved into stone has been erased by time. It may be the single most enduring object our civilization has ever created, riding on a spacecraft currently running on less electricity than the bulb above your bathroom mirror. Now back to the science, because one more piece deserves to sit at this story's center. The persistent plasma hum detected since 2017 isn't just a strange anomaly. Researchers say it represents the first continuous, real-time measurement of interstellar plasma density our species has ever obtained. Before the signal appeared, scientists could only capture scattered snapshots, readings triggered by specific events like shockwaves from solar eruptions rippling out to the heliopause. Those measurements had value but were sparse and disconnected, like understanding an entire continent's climate by checking one thermometer once a year in one town. This persistent hum offers something much closer to a continuous broadcast, a running picture of interstellar plasma as the spacecraft drifts through it year after year. And that picture reveals interstellar space is anything but a flat, unchanging backdrop. It has texture. It has structures built from charged particles and magnetic fields stretching for millions of miles, interacting with our solar system's boundary in ways no Earth-based model could ever have foreseen. The space between the stars is not empty. It is full, active, and has a kind of physical character we are, for the first time in human history, only just beginning to actually read. There's a central question the scientific community hasn't resolved. This signal has two possible explanations, and researchers haven't nailed down which is correct. One possibility is thermally excited plasma oscillations, the natural vibration of charged particles interacting with their environment. That alone would be significant, but it would slot neatly into existing theory without demanding a rebuild. The other possibility is something called quasi-thermal noise, a distinct physical process that encodes plasma density and temperature information in a subtly but crucially different way, one that would force existing models of the interstellar medium to be substantially rewritten. Settling this requires either more data from Voyager 1, which produces less every year as instruments go dark, or an entirely new mission purpose-built to study interstellar space. No such mission currently exists or is funded. Even if one were launched today, it wouldn't reach the heliopause for at least 25 years. When Voyager 1 finally falls silent, the question it raised will remain wide open, and the only real-time window our civilization has ever had into interstellar space will close for decades. That silence is coming. The exact date isn't fixed, but the direction is. Every year the power drops further. Every year another instrument goes offline. Every year the team at JPL faces harder decisions about what stays running. Sometime in the early 2030s, the last instrument will dip below its operating threshold, and the final signal will begin its lonely 24-hour journey home, arrive, be logged, and nothing will come after it. From that point on, Voyager 1 will keep drifting silently at 38,000 miles per hour, carrying its golden record through the dark, passing through regions of the galaxy no human eye will reach for tens of thousands of years, continuing a journey that began on a September morning in 1977, and when a small group of engineers pointed a machine at the stars and expected it to last 5 years. Here's what deserves to stay with you. Buried in the middle of this story is a fact easy to overlook amid the physics and engineering drama. Right now, in 2026, the only functioning scientific instrument humanity has ever placed in interstellar space is 48 years old, built with technology predating the personal computer, running on less power than the bulb above your kitchen stove, and it is currently reshaping how we understand the universe and our place inside it. We've since built things far bigger, far more powerful, far more expensive. And none of those things have told us what Voyager 1 is telling us right now, because none of them shared the one quality Voyager 1 actually had. The sheer stubbornness to keep going long enough to actually arrive. There are questions about the universe that can only be answered from inside it, not from a telescope on the ground, not from a satellite circling Earth, not from a mission to Mars or the asteroid belt, only from a machine that physically crossed the heliopause and entered the true space between the stars. We have exactly one such machine. It is old. It is dying. It runs on 4 watts of power. And as long as it keeps transmitting, we need to keep listening, because once it falls silent, the answers to some of the most important questions we've ever asked will go quiet along with it, for at least a generation. The signal is still arriving, stretched across 15 billion miles, delayed by 22 hours of travel time, carrying word of a universe stranger, more turbulent, more interconnected, and more extraordinary than any model built from the surface of Earth ever managed to describe. One machine, 4 watts, one single chance to listen closely. The only question left is whether anyone is actually paying attention. If stories exactly like this are exactly what you come here for, hit subscribe and turn on notifications, because we're heading even deeper into the edges of what science actually knows next time. Drop a comment telling us what surprised you most in this one, and share it with someone who needs to hear it, because a story like this deserves more attention than the silence it's currently getting.